Sorry if this gets a little bit technical at times. I'm also a math user, so I'm going to get lost at some point. So, welcome. Thanks for coming. You've already heard from Eileen what IMBER is, Integrated Marine Biogeochemistry. Just for a sec. Okay, so I'll give it another shot. So we've heard of Eileen what IMBER is, basically, and for most of the time of IMBER's background, people have assumed that's meant just the geophysical side of the world and the ecological processes that are in that. So certainly my background has been from that side. We think about some of the earliest examples of definitions of ecosystem, then it's all about physical and chemical processes. But as we've learned the hard way over at least the last decade, if not the last century, it's forgot that the humans are a part of the system too, and that has to be integrated in if we're actually going to move ahead. So really we need to think about a much broader set of activities than just the geophysical and biological ones that we've thought about in the past. We need to start to really think about that whole socio-ecological system. That's why we brought this summer school together, because basically if you counted up the number of people who do this kind of stuff in the world and did an IUCN rating, it would be the most endangered species on the planet. So we need to get those numbers up, and we need to get them up fast. So this is the idea, is to try and see the population that can help us break that wave and then bring that into society. So hopefully we don't put you to sleep and you actually pay attention this week, or we can get the whole thing moving. It's also a requirement by my mother, as much as anyone, that I forewarn you as an Australian, I will swear at some point. I promise not to do it often, or at least I'll try not to do it often. I'm sorry if that causes any offence, I just really can't help it, it's a part of my language. I'm also suffering very major jet lag, as probably many of you are, so we don't mind if we see the odd yawn, we will understand, because we'll be doing it just as much as you are. But what we want to do is, because of that, we want you to break down any fear of asking questions. There's no such thing. Well, the silliest question is the one that you don't ask that then leaves you far behind as you get lost, okay? So feel free to ask questions. The other expectation is that it's going to be hands-on. So while they won't be overly complicated models that you'll be playing this week, there is an expectation that you'll join in and play with the models and start to think about what they would look like for a system that you use. So we want this to be much more interactive. Also, I call my own children their wrong name. I've called my daughter the dog's name on numerous occasions. So, again, apologies if I use the wrong name or mispronounce the name. I grew up in a small rural town in Australia where the most complicated name is Francis. So I'm going to mess up someone's name at this point. So please don't be offended, it's not intentional. And feel free to call me the wrong name all week as well. So basically, what are these kind of models would form? Well, I'm going to ease you in by giving you a whole bunch of information about a system that you probably already know. That's just because it's early in the morning and I was trying to give everyone time to wake up. But basically there's billions of dollars that come from the marine system every year from oil and gas. These numbers now are a couple of years old, but they're quite large numbers from oil and gas. They're growing and doubling actually all the time. Tourism is surprisingly the second largest sector that uses the marine and coastal zone. Fisheries comes in at number 4. Shipping is growing quite a lot. 80 to 90% of the world's transport still happens by ship, and that's not really going to change anytime soon. But all of that's dwarfed by the amount of ecosystem services if you start to cost them up. So this is updated, it's now again a couple of years old. But when half of the oxygen you breathe comes from the oceans, it's a fairly significant service that they provide for us. It's not just, the other thing that I'll apologise for is I have a much larger computer screen and it's going to keep cracking a little bit. But it's not just the food that we get from the system, it's also stuff that's very hard to put into monetary terms, such as culture and relaxation and that kind of stuff. But they are some of the biggest drivers around the way that people value and use ecosystems, so they have to start to be taken into account. The thing is, and the reason that we're starting to realise these pressures are important is because we live in the Anthropocene, so we've now had a big influence on our planet. So this is a picture of the International Space Station flying over Europe. Each one of those is a major European city, and you can see we've effectively made our planet on fire if you just look at that image. It's quite a stunning little movie that you can find on YouTube. There's also been quite a lot of indices that people have looked at, and you've probably all seen this before, but basically if you think about the ways that we use our world, whether that's telecommunications, number of McDonald's restaurants, water use or population, since about 1900 to 1950 they've all skyrocketed at an exponential rate. The influence that this has had on our world, so whether that's water use, biodiversity decline, the number of major floods, any sort of major indicator of ecosystem response or environmental response you can think about, they've also spiked. One of the biggest ones that most interested me was the ozone hole. The reason that's interesting to me was it's actually an example of how we shouldn't be overwhelmed by these indicators, that there is hope for action. So the ozone hole back in the 1970s was considered an even bigger issue potentially than climate change. No one figured out how they were going to solve it, and it was human action. They just turned around and did what they had to do to fix the problem. Ironically, that time it was Europe dragging its feet and America pushing forward. We seem to have reversed that a bit this time around in responses, but people got out and did things, so it's not impossible. All of this is set behind the background of the fact that we're making the world very different. It's been a long time. So 80 million years ago was at this end of the thing. So this end of the thing that's 80 million years ago, you're flying forwards to now at that end of the world. You can see that the open dots are actually observations from geological things or cores. The solid dots are what we're predicted to do. So you can see we're doing a sharp hook in the way that we're going to make the world be environmentally. So whether that's acidification or temperature. All to a background of more than 7 billion people. So that's going to have some fairly significant effects. So this is the amount of temperature increase that's happened off Australia already. We're predicted to change by up to 4 to 5 degrees off Australia by 2050. Sea level rise is going to change by potentially more than a metre. The Southern Ocean is likely to be corrosive to aragonite all the way to the surface by the middle of the century, as will some local areas like parts of the Great Barrier Reef, for instance. So we're radically changing the ecological and physical side of the system. So we can see that in the case of reefs, so over a third of those are already damaged, almost beyond repair, I would say. A third of them are highly threatened. And a third that are roughly in good condition happen to be in spots that aren't likely to be very hospitable for them by the middle of the century. So last week there was actually a call put out by 3,000 coral reef ecologists to say we need to do something. Again, there's a mixture of hope. So there's people that certainly think that they can turn things around with coral nurseries and things like that. But on the other hand, there's some quite senior thinkers who advise governments who are saying, right, we need to prepare communities for what they do once those reefs are gone. So they're trying to think ahead of what kind of ecosystems will come into place, or what ecosystems they should actually see, so that people don't lose their coastal buffers, their food sources, and all those kind of things. And again, there's a message of hope with the fisheries, as odd as that sounds. So there is a third of the world's fisheries that are still, where overfishing is still happening, they're still depleting them too much. But the other 2/3, the overfish just means they used to be overfishing. Their stock's still depleted, but it's actually turned around. People have changed how they're using the system. And there's another third that's recovered or was never fully exploited in the first place. So the messages that we often get on the news that all the world's going to hell in a handbasket fisheries-wise, that all the fish in the sea will be gone by the middle of the century, doesn't actually reflect the fact that about 1995 there was a change in people's attitudes, both the general public and the governments, and it really has been a switch in fisheries management to be more and more sustainable. It's actually a positive message, which again gives us hope that we can actually do something if we bring people into this. So a background to this though is that biodiversity is turning over, and that's something that both human responses will have to get used to. We'll have to get used to looking at a different set of fish on our plate, for instance. So if we look at the makeup of global fisheries, you can see there's more and more pelagics as we go through time. In Antarctica, places like Antarctica and others like the Gulf of Thailand, there's been an enormous shift in what we actually fish, going much more to invertebrates. The reason that that's a challenging thing for all aspects of science and society is we don't know an awful lot about the oceans. So as early as late as 1870, we didn't think that anything lived deeper than the photic zone. And pretty much we've just learned more and more as we go through time. Every single cruise that goes off a place like Australia finds more species than were ever known to science in in Australia recently where 99% of the animals have never been seen by scientists before. And it's a fairly developed country that tries to get a handle on its biodiversity. So, and if you also think about the census of marine life, where they try to catalogue everything they do, if you think of the world's oceans, this is the coast over here, this is the seabed, this is the surface. This is the bit that we know. We haven't sampled the bits in the middle because we can't get to them with sensors. So there's a huge gap out there in what we do and don't know, which is going to complicate things as we try to model them. We're in the midst of the 6th great extinction on the planet, partly or majorly due to what we're doing to the system. While we can't predict what that world will look at the end of that extinction, we do know from past ones that a major component of the system will disappear. That's what's happened every other time when it's been an asteroid strike or basalt eruptions or whatever. So we know the system's going to change enormously. We have to be responsive to that if we're going to survive. So that's when you get into management. This is where the human stuff really has to kick in. People have to understand why they want to do things and how they'll respond if you're going to be on top of what will be a sustainable management. So this is actually Hammurabi's stele that was chiselled out about 5,000 years ago. On that stele is complaint about fisheries management, that stocks are overfished, that he doesn't know how to control fishermen short of beheading them. And it's not a problem that we've necessarily fixed in the last 5,000 years. We just seem to repeat it. So it's something we do have to get to grips with. The problem being is a trade-off. It's not a simple optimisation, maximisation problem that humans are very good at. It's actually balancing trade-offs, which we're not very good at. So it's not just the environment, it's also the economics, but also the social aspects of employment and interactions and the freedom of people to actually change life into a lifestyle that they're accustomed to. So the role of science in that is to support decisions. So whether that's a destroyed coral reef that can actually be recovered, or in the case this is a bay in Tasmania where I live, it's actually been quite well recovered now. But the point behind that was that we didn't get anywhere until there was a marriage of social community understanding and science. So just telling them all science doesn't help if they don't know how to use it. So this is where the models come in. So in all aspects of human life now, flight simulators of one form or another help educate people or teach people how to deal with complex situations, whether it's brain surgery, fixing cars, learning to fire rocket launchers, driving planes, learning to ski, which I think got that one, splat roll. So yeah, this is where our models can sort of fit into this. We can give people effectively flight simulators to fly the world and see which versions crash and which don't. So, and the reason that this will work, or has worked well in my experience, is that humans are natural storytellers. So the first one up there is what I think Manhattan looked like 400 years ago based on evidence, a picture of a couple of years ago, and then an artist's impression of what it might look like 300 years into the future. So people like to tell stories about the past and the future. So the only difference is now that we're going to base those stories on science and make them internally consistent. This is something that started quite a while ago. So if we think of the climate, back in 1896, Arrhenius got a divorce, and as all good mathematicians do, he threw himself into a problem to cheer him up. He thought he'd calculate global climate layer by hand for 6 months. And in the end, he was actually trying to look at ice ages and what would happen if there was a decrease in CO2. But being a good scientist, he said, I'll look at an increase as well. So he spent another 6 months. And at the end, he decided it would be about a 5-degree increase if he doubled CO2 at that time. And to be honest, that's about what our models say today. So at least we've cross-checked ourselves. Climate models have got a lot more complicated since then. So if you think about the history of climate models, they've sort of started off with mostly atmosphere and ocean, and they've added bits as they've realised there were feedbacks that were really important. We're getting to here, and we need to get the people obviously in there. So there's some people bits that influence these, but there's no explicit people that are listed in that diagram. So for those of, we've got quite a mixed background in the audience, so for those of you who are not climate modelers, and for those of you who are, excuse any gross generalisations I'm about to make, but basically you have a net grid that represents the oceans and the climate, the oceans and the atmosphere, and then within each one of those grids represent the processes that drive